All right. Derivatives. We're finally at calculus, right? It only took us however long to get there. Okay. Derivatives. You might have seen this already in AP Calculus. If you might have already seen it in AP Calculus, probably. So most of this is review. Okay. Um, we call it sometimes differentiation. Differentiation. Okay. And the result is called a derivative. So if we have, for example, a function f of x and we take the derivative of it, okay, then we call that f prime of x. Okay, so if we differentiate this function f of x, then we take the derivative of it, which is that you're going to hear derivative, you're going to hear differentiation. You have to understand that those two terms are equivalent to each other. I do really quickly want. Oh, I'll make a note on the notation here, on the notation that we use in AP Physics. There's two ways to notate. Okay, there's two ways to notate derivatives. Okay, the base function, and you can kind of see it up here. The base function is usually y equals f of x. Okay, and the derivative. Okay, and the derivative would be y with a dot over it equals f prime of x. So either way, if you see a dot over something, that means it's the derivative of whatever the dot is over, and then f prime of x is the derivative of f of x. And then if it's like the second derivative, it's f double prime. If it's like the third derivative, it's f triple prime, and so on and so forth. Okay, derivative is something that gives you the slope. So it actually technically gives you the slope of the tangent line at that point. So a line tangent to that point gives you the slope. But it gives you the slope at a given value of x. In physics, you really just need to know that it gives you the slope, okay? It also represents the rate of change, okay, of that function at a particular value of x, okay? So here's an example right here. If we're taking the derivative at different points, we're taking the slope there. We're basically kind of looking just at that point right there, and we're taking the derivative of it. Okay. So you'll notice that so like f of -4, f of x, where x is equal to -4, that gives you 4, which is the value of the function, the y value of the function at that for that x value, and then this is the slope of the function at that same x value. So you'll notice right here, -4, right? The y value is 4. The slope is going to be -2. Okay, the slope there. Okay, and it's like right at that point. Okay. It only takes 2 points to establish a line. Okay? It only takes 2 points to establish a line and calculate a slope. Okay? All you got to do is take 2 points on there, and you'll notice that, like, for example, this is a parabola, right? Or half of a quadratic function. For something like a quadratic function, you can approximate the slope as just taking the slope between 2 points, and those 2 points can be anywhere near or far apart from each other. But it's typically more accurate just to do the derivative, right? For a quadratic function, you'll notice that these two slopes, even though we would approximate them to be the same, right? This part right here, doing the derivative is a lot more precise because we're getting 2 points really close to each other. This part right here, you'll notice, is not like these two slopes are not the same, right? This is a more accurate answer. This is not as accurate, okay? Okay, constant rule. So the first and easiest rule for derivatives is this, okay? If your function is always equal to a value, okay, to just like some constant value, like let's say f of x is equal to 5 at all points, then the derivative of that is just equal to 0, okay? And f prime of x would be equal to 0, right? That's two ways to write the derivative, okay? So think of it like this, right? If your function is equal to a constant value, then this is, f of x, and this is your x value, right? Well, then the way that this graph is going to look is it's just going to be a flat line at that value, right? Okay? It's just going to be a flat line at that value. There's no slope. Okay? So derivative equals 0. Okay? Okay. The power rule is one of the most simple rules, but also one of the most important rules to understand when it comes to derivatives. And it's simply f prime of x is equal to, so if our function is c times x to the nth power, okay, then f prime of x would simply be c times n x to the n minus 1th power. So you're taking the power and you're multiplying it by the constant. You're multiplying it in front of the x, and then you're subtracting 1 from that power. Okay, that's how that works. The addition subtraction rule is that if you have y is equal to f of a function, one function plus or minus another function, then all you got to do is take the derivative of those two functions separately, and then you can still add or subtract them just fine. Okay? The constant multiple rule, if you have a constant in front of a function, so if it's like a function multiplied by some constant like 5 or something, then you don't do anything to the constant. You leave it be. Okay? So the constant stays there, and then f prime of x. Okay? Okay. So an example, right? An example, and you'll see this here in just a second, right? If I have a function y equals 2 x to the 4th minus 5x to the 8th plus 7x to the 4th, okay? Then if I took the derivative of that, I take the exponent and bring it down to multiply by the constant in front of it. So 4 times 2 is 8. And then I decrease this by 1. So x to the 3rd minus, okay, 8 times 5. Okay, that gives me, so 8 times 5. And I just realized I actually wrote it wrong in the key. I wrote 9. I guess I mistook my 9 for a 5. Okay, but it works out just fine anyway. 8 times 5, that should give me 40, right? 40x to the 7th plus 4 times 7, 7, 14, 7, 14, 21, 28, right? 28x to the 3rd, okay? And then you could combine the like terms, right? That's how you do it. Pretty straightforward, nothing too crazy, okay? Like I said, you've probably seen this in calculus before, so this is probably not anything new to you. It's probably not anything too crazy, okay? Trig function derivatives, okay? You do need to know some trig function derivatives, okay? It is important to know how those work. So for example, if you have the derivatives of trig functions, so like cosine of x, okay? So the derivative of sine of x is simply just cosine of x. Now, that does not mean that the derivative of cosine of x is sine of x. It's actually negative sine of x, okay? So there is a little bit you have to think a little bit for that one. For the exponential and logarithmic functions, so if you have a natural log, okay, the derivative of natural log is simply 1 over x, or you can also say x to the negative first power, because that's the same thing. Those are equivalent. And then the derivative of e to the x is simply just e to the x. Okay, nothing too crazy. Okay, let's find the derivative. Okay, all we got to do, right, for the first one, okay, first one's pretty straightforward. All we got to do is take our exponent and multiply it by the constant and then decrease it by 1. Okay, so then 4 times 3 is going to give me 12. Okay, f prime of x is going to be equal to 12x and then decrease it by 1. There you go. That's all you got to do. That's a derivative. Congratulations, you just did it. You did calculus, okay? What about the next one? Okay, so this is going to be 4 times, okay, if you don't see an exponent, if you don't see a constant in front of the x, that means that it's 1, right? Because it's implied to be 1 times that. So it would be f prime of x would be equal to 4x to the 3rd plus 6x to the 2nd, okay, minus 8x to the 1st, and so I don't have to put an exponent on that. 3, okay, so this has an understood exponent of 1, right? And then you bring that down. That's just going to be plus 3. And then now that exponent becomes 0, which is just, so then x to the 0 would be 1. Doesn't matter what x is, okay? So then that just goes away. We don't have to worry about that. And then plus 7 is a constant. It's, if you think about it, right, it's technically got x to the 0th power in front of it. And when you bring that 0 down, it just turns into 0. The whole thing goes away. So there you go. Okay. Oh gosh, Mr. Mitchell, this problem looks terrible. It's not that bad. Okay, let me show you why. Because if you rewrite this problem so that everything has exponents instead of these ugly, ugly square roots, then you would get x to the 1/2, okay, plus 4 times x to the 1/3 minus 2x to the negative 1 plus 3x to the negative, or sorry, 1/3, sorry, 1/3 x to the negative 2, okay? And that makes it so much easier to solve because now you have exponents on everything, and you can just power rule it, okay? So when I do this, okay, I'm getting 1/2 x to the negative 1/2, okay, plus, and you do have to subtract 1 from everything. You're not subtracting by halves or anything. You're subtracting 1, the whole number 1, okay? 4x to the 1/3. Okay, so this would be 4 over 3x minus 2/3, okay? Minus, so then we would do the negative 1 times that. That would actually turn this into plus 2x to the negative 2. And then multiply by the negative 2, you would end up getting negative 2 over 3 x to the negative 3rd, okay? Oh, what a mess, right? You're like, oh my gosh, Mr. Mitchell, that's so much stuff. So much stuff. Yeah, it is. I'm sorry. Okay. And then for the last one right here, these are constants, right? So notice that the 6 and the 2 are constants, so we don't need to worry about them, right? If this is like our function f of x, okay, and this is our function g of x, okay? So then, right, we have the constants. We just leave them alone. Don't touch them, okay? So this is just going to be, it looks crazy, but it's actually not that bad because you would just do 6 times the derivative of sine x, which we got earlier was cosine x, okay? And then the derivative of cosine x is negative sine, so it's actually going to be plus 2 sine of x, okay? See how that works out? Easy derivatives, okay? Easy money for you, okay? Okay, chain rule. Chain rule is one of the more confusing rules in physics, and it does get pretty confusing, especially when we introduce U substitution into integration. Okay, but if you have I call this a nested function where you have f of g of x, so g of x is nested in the f of x. Okay, then what you can do instead, this is a nested function. What you can do is you're just kind of unwrapping that function. So the derivative of y would just be f prime g of x, okay? So we take the derivative of the outer function, then we multiply it by the derivative of the inner function, okay? So we're kind of unwrapping it in a way. Do you see how we're unwrapping it? When we take the derivative of the outermost part and we kind of unwrap that, and then we get to the innermost part, take the derivative of that, and we've unwrapped the whole thing, right? Now let's say that you have a function f, which is a function of g, which is a function of h, which is a function of k, and you have this insane thing, okay? This is like absolute torture, right? Then the derivative, you're just unwrapping it. This is like a present that's hidden in like 4 boxes. You have to tear through the first box, you get another box, tear through that box, get another box, tear through that box, another box, tear through that box to get your present, right? So that's what we're going to do. We're basically unwrapping the function and getting the solution. So f prime, okay, of g of h of k of x, okay? Then we have to multiply that, okay, by g prime of h of k of x, okay? And see how we're unwrapping it. When we take the derivative of that function, we have unwrapped it, right? Okay, multiply that by h prime of k of x, okay? And then multiply that by k prime of x. And then boom. That's all you got to do, okay? I don't think you're going to see anything that's crazy because that's just a lot, but we're trying to get the point across that you're just unwrapping the function, right? You're just unwrapping it, okay? Nothing too crazy. The product rule is that if you have two different functions that are being multiplied by each other, u and v, okay, the derivative is found by using the functions u and v and their derivatives. So f prime of x, okay, would simply be u prime of x times v of x. So we leave the v alone here. And then we have to add to that u of x times v prime of x. Okay? So they're each getting their turn getting a derivative. Okay? If it's the product of several functions, so there's t, u, v, and w, then this is going to look like a huge mess. But basically, each one gets its turn being a derivative. Okay, so you would do, t prime. I would do t prime times u times v times w plus t times u prime times v, and I'm just using simple notation. I'm not writing the of x's and stuff like that. Times w plus t times u times v prime times w plus t times u times v times w prime. Okay, you get the point, right? And that's just like that's cruel and unusual punishment at that point. Okay. Okay, you would just do that for however many you have. The derivative of y, I'm going to tell you right away. I'm going to give you right off the bat. I'm going to tell you this. I'm going to skip this last one. You know why? Because it's terrible. Okay, I'm going to skip the last one. So I'm skipping this one, but I will tell you what you would end up getting if you calculate the whole thing out. And the main reason why we're not doing that is because it's just a lot. Okay, you would get that the derivative of this is cosine times natural log. Okay, or cosine of natural log of tangent or inverse tangent of x over x squared plus 1 times the tangent negative 1 of x. And that's a mess, right? You would have to know a lot more calculus to be able to do that. So we're not expecting you to do that. Well, the first part, I'm going to have to use the chain rule. You know why? Because I have two functions here. I have an exterior function. Okay, here's my exterior function is the sine, and then my interior function is the x squared. Okay, so then what I'm going to do is I'm going to now use the chain rule. Okay, so I take the derivative of the exterior function, that's cosine, and I leave the interior in there. Okay, and then I multiply it by the derivative of the interior. Derivative of x to the second is just 2x. There you go. And you don't have to simplify it any more than that. I'm satisfied with that, okay? This is also chain rule. You know why? Because you have an interior and exterior function. Believe it or not, your exterior function is actually this right here. And your interior function is the sine of x. Okay? So now, when I take the derivative of it, I take the exterior function, which is x to the x squared. That's what it is, x squared, right? So I get 2x, okay? 2 sine of x, okay? And I multiply that by the derivative of the interior. Derivative of sine is cosine. Okay? And fun fact, that's actually a trig identity, right? You could say that that is sine of 2x. Okay? That's a trig identity. Okay, but you don't have to. Okay, right here, sine x, natural log of x, you have to use the product rule for this one. Okay? And in using the product rule, right, each one gets its term being the derivative. So we would do the derivative of sine of x, okay? That's going to be cosine of x, okay, times natural log of x. So that's the first term. Sine got its term being derivative. Now it's natural log's turn, okay? So then we would do sine of x times the derivative of natural log, which is 1 over x, okay? Pretty straightforward. Okay, if you have to take the second derivative of a function, okay, all you are doing is you are just doing the same thing twice. You're just doing the same thing you just did. So the second derivative of function f of x is noted as f double prime of x, or you can also see it as d to the second power d2f over dx squared, okay? Because the first derivative is df over dx. Okay, so the second derivative is this. Okay, another way to denote it is, for example, y with 2 dots above it. So every dot above the letter is one level of derivative. So 2 dots would be a second derivative. Okay, this is called the derivative of the derivative, or the second derivative of derivative. Okay, or second derivative. Now, to find the second derivative of this function right here, okay, all you have to do is take the derivative once, and then guess what? Take the derivative twice. That's all you gotta do. Nothing too crazy, okay? So to find the first derivative, okay, all I would do is do y, so bring the 3 down, so you get 3x, and then subtract 1 from the exponent, so 3x to the second, okay? And then minus 27, okay? Because this has a 1 up there. 1 times 27 is 27, and then it becomes 0, so then x to the 0th is 1. Okay, now to find the second derivative, I just do the exact same darn thing. Multiply, bring the 2 down, so that gives us 6x, okay? And then the 27's gone. It doesn't even matter. It's gone. That's all you got to do for the derivative, okay? So that's the second derivative of that function, okay? You need to know your graph rules for derivatives, okay? And I provided you a couple of them here, okay? You should know that if you have, for example, if you have, for example, the graph of the base function, and has a positive slope, and that means the first derivative of it is positive, okay? So the slope, whether it's positive or negative, tells you things. So slope tells you things about, the first derivative tells you things about slope. The second derivative tells you about concavity. Okay, if the second derivative is positive for that function, then it would be concave up. If it's negative, it'd be concave down. Okay, so second derivative tells you things about concavity. First derivative tells you things about slope. Okay, okay. And then finding max. Talking about extrema. Okay, it's extrema is pretty easy to understand. It's nothing too complicated. Okay, but a critical point is a value of x such that the derivative of x. Oh, that looks like a double prime. It should be 1 prime. Okay, where the derivative of x is equal to 0. So that means flat slope. Okay. A critical point can be one of 3 things. It's either a local maximum, okay? Either it could be a local maximum, which is where a point where the value of f of x has nearby points that are lower. Okay? An example of a local maximum right here would be this part right here, because you notice that the slope is 0, okay? And the nearby points are lower than it, okay? A local minimum is where the nearby points are higher. Okay? Local minimum is where the nearby points are higher. Okay? So you notice, all right, the nearby points are higher. Great, cool, awesome. Okay, that's a local minimum right there. Okay? And then finally, an inflection point is where the function changes concavity. Okay? It changes concavity. So it goes from one concavity to the next. This is an inflection point right here. You notice that the slope is 0. Okay? That's because it's changing direction. It's going from a positive to negative or negative to positive. Okay? So what that means, right, is that you can see the concavity changes because right here it's concave down, and then right up here it's concave up. Okay? You see how that works out? Okay, the final thing I want to point out for this, and I'm not even going to really write anything for this, is that there are other conditions to have a critical point if the derivative is undefined. However, we don't do that in physics. Okay, here's examples, right? Here's examples of what you might see. If you have the graph of 1 over x squared, right? Then if you have like an asymptote right here, well, the function is undefined at that asymptote, so there shouldn't be a derivative there. If you have something like this, this is where you might have a section of the graph that is perfectly vertical. If it's perfectly vertical, then the slope is undefined. Okay, you can't have a perfectly vertical slope. There's no real value for it. It's undefined. Okay, so you wouldn't have to worry too much about that. And then finally, here you might be thinking, well, there should be a slope there. Except normally most graphs they are kind of curved and slowly reach. But you notice that what's happening is it has one slope here, and then right here, it's kind of it very very suddenly changes directions. Most graphs, pretty much all graphs we look at physics, like the example right here, you see how it slowly kind of changes its concavity and stuff like that. This one just very suddenly, very sharply turns, and that would not be okay either. That would be it would be undefined. Okay, the slope would technically be undefined there, even though it looks like it would be 0. Okay, well that's that. That's derivatives. Come back next time for integration. All right, have fun.